this chapter, chapter 9, we are going to discuss logistic regression. In the past chapters, we discussed linear regression models because the response variable was quantitative. So we used to have predictor variables, using these predictor variables to estimate the response variable, which was numerical or quantitative. But sometimes you have the response variable that contains classes or categories, in a way that the response variable is not quantitative, it's qualitative or categorical. So like the qualitative response for an observation can be referred to as classifying that observation, because it involves assigning the observation to a category or a class. So I give you an observation, then I tell you that we have these predictors. For instance, if we're talking about patient has high blood pressure, has high BMI, body mass index, he's got problem with his diabetes, he has many other complications. So I'm going to ask you that this person is going to have a heart attack or no. So the heart attack is the response variable in this case, and it has two categories. A person is going to have a heart attack or he's not going to have a heart attack. So we're assigning the observation to a category. So in this case, we're talking about classification problem. So this kind of problems, we call them classification problems. In the past, in chapter 7 and 8, we talked about regression problems. When the response variable is not numeric, it's categorical, the problem is classified, or it's called to be a classification problem. And the methods used for classification first predict the probability that the observation belongs to each of the categories of a qualitative variable as the basis for making the classification. This is exactly what we're going to do. We're going to look at the probability that a specific observation belongs to each category. Examples: if a person arrives at the emergency room with a set of symptoms that could possibly be attributed to one of the three medical conditions, which of the three conditions does the individual have? The predictor in this case is all of the symptoms. What is the response variable? We're going to classify this person in one out of the three conditions that this person may have. Or if you have an online banking service, must be able to determine whether or not a transaction of being performed on the site is a fraud or no, based on many variables such as IP address, past transaction history, and so forth. So in this scenario, what are the predictor variables? The IP address, past transaction history, maybe the place, and so on. So what we are trying to do, if you are given all of this information, we are trying to classify this observation whether to be a fraud activity or no. There are at least two reasons not to perform classification using regression method. Number one, the regression method cannot accommodate a qualitative response with more than two classes. Sometimes the qualitative response contains more than two categories or two classes. The regression method cannot do this. Even if we have a classification, or if we have a qualitative response that contains two classes, the regression method will not provide meaningful estimates of the probabilities. One type or one techniques that we are using to solve classification problems is using logistic regression. Logistic regression is one of the techniques to do this, because we have many other techniques to solve classification problems. What is the method we are using to estimate the logistic regression? If you remember, for the regression analysis, linear regression analysis, we used ordinary square method to estimate the linear regression method. But for the logistic regression, we're going to use something called maximum likelihood estimate. And the interpretation of the betas may be tricky here. So that's why let's go over this. The probability of success, again, we are going to predict the probability here. What is the probability that this case is going to be belonging to this category? So we are going to get probabilities. So we are going to estimate this logistic regression model. P equals the E exponential of beta 0, which is the intercept, plus beta 1, x1, etc., divided by all of this. And we are going to estimate this. This is the model that we're going to estimate, and this is the estimated model. P hat, the predicted probability, is going to equal to all of this. Okay, let me skip the example because we're going to go over the example. The odds of the event. The estimated coefficient of a logistic regression model does not allow us to determine the partial effect of a predictor on the probability. Yes, this is a problem, that the estimated coefficient doesn't allow you to look at the betas. We cannot interpret these in the way that we used to. So to interpret these, we're going to use something called odds. Odds is something that you have been or heard about, which is used a lot in sports and gambling, right? For instance, in sports, if the odds of winning are 3 or 3-1 odds, that means the team has 3 out of 4 chances of winning. And how do we calculate the odd? The odd is the probability divided by 1 minus the probability. Also, we can calculate the probability of winning by dividing the odd over 1 plus the odd. So, which is the probability of winning. If you have a 3 as the odds of winning is a 3, what is the probability of winning? It's a 3 divided by 4, which is 75%. And if you notice that as the first one increases, the second one increases. If the odd increases, the probability increases, the opposite way around. The odd value of 1 means that the event is likely to occur as not. We have 50-50 chances if the odds is 1. If the odds is greater than 1, this means the event is more likely to occur than not. Conversely, an odds value less than 1 indicates that the event is less likely to happen. Why odd? Why do we care about the odd? Because this is the one that we're going to use to interpret the regression coefficients. The regression coefficients will be using odds for interpretation. As we said, the odds equal the probability over 1 minus the odd. If you do mathematical, applications, just mathematical equations, you're going to end up having ln of odd, or the log of odds, equals b0 plus b1 times x. And this reminds you of what? This reminds you of the equation, the exponential equation, the exponential transformation that we did in the regression model. Now we can interpret the b1, because the goal is to interpret b1, b2, b3, which is the coefficients of the x's, right, of the predictors, right? How to predict this? b1 times 100 is the approximate percent change in the odds when x increases by 1 unit. And it's similar to what we did in the regression model when we had exponential transformation. The next point we're going to discuss is about how to measure the performance of the model. In the regression model, we cannot rely on the goodness of fit measures like SER squared, adjusted R squared, to assess the logistic regression model because we don't have residual here. But we can use many other techniques to assess the performance of the logistic model, such as the accuracy rate. One of the things that we can do is the accuracy rate. Once you calculate the probability for an observation, if I give you an observation, then we found that the probability of this person is going to default on loan, like the expected probability is going to be like 0.6. So you have to classify this observation. So this guy is going to default on loan or no, if the probability that he's going to default is 0.6. So at the end of the day, because the probability is greater than 0.5, you're going to classify him as yes. So he's going to default 1. You're going to give him a value of 1. If you get a person that with the expected probability that a person is going to default is 0.2, then this person has a low chance to default on a predicted low chance to default on loan. Then you're going to classify him as a 0. So that's why what we do when we do classify all of the observations using the cutoff value, which is 0.5, greater than 0.5 is yes, less than 0.5 is no, then we can compute the accuracy rate to assess the performance of the logistic regression, which is number of correct predictions divided by the total number of the predictions. Not only the accuracy rate, we have any other techniques. As you remember, we talked about predictive power of a model and assess the performance of the model in the training data as well. We use cross-validation techniques. Cross-validation techniques, we have both the holdout method and the k-fold cross-validation method. Also, we are going to use the accuracy rate as a performance measure. Also, we're going to use something called sensitivity and specificity for performance measures. So we have 3 performance measures: accuracy rate, specificity, and sensitivity. And we are going to use the predictive power using the cross-validation techniques, the one that we learned. And the accuracy rate report the percentage of correctly classified observations for both target class and non-target class. And what is the sensitivity? Is the proportion of a target cases that are classified correctly. What is the target class cases? The target class, for example, if we're talking about people who are going to default yes or no, Your target class basically in this scenario, in this application, is people who are going to default. You don't want to lose your money, right? So this is your target class. This is the one that you're going to focus more. So to calculate this proportion of people, then this indicator called sensitivity. The other proportion for the non-target class, the people who are not going to default, this we call it specificity, right? So we're going to calculate these two things. The last slide, or the last thing we're going to talk about, is sometimes we have imbalanced data. Sometimes you have so many ones, a few zeros, or the opposite way around. So this is referred to be having imbalanced data. Severe imbalance is challenging for assessing performance. And this is a good example. When detecting fraud, the response variable is 1 for fraud, which is my target class, and 0 is otherwise, non-target class. And we here care about what? Identifying fraud cases. But number of the fraud cases normally is very small. It's about 1% of all of the cases. So when you develop a model and classify all non-fraud cases, or when you do the classification, the non-fraud cases, all of them will be classified correctly. But you're gonna miss most of the fraud cases, and this is not useful. And this will give you a problem with why we are not classifying the fraud cases correctly. So what we do in this case, we're using different cutoff value. Using different cutoff value would be appropriate, and cutoff value, maybe we can use it equal to the proportion of the observations in the target class, which is important. This would improve the sensitivity even though the accuracy may be compromised. So this is important to understand, and how to deal with the imbalanced data. In the next recording, we're going to go over all of these concepts in one single example. Thank you.